Hello learners, welcome to Unfold You, your favorite digital learning platform. This is Priyanka, your mathematics mentor. In this module, let's unfold the topic of real numbers. We have already studied about different types of numbers in our earlier classes. Let's recall them in brief. First were the natural numbers. These are the numbers starting from 1 and continuing up to infinity. These are denoted by the symbol n. Next are the whole numbers. These are the set of numbers that include 0 plus the natural numbers. These are denoted by the symbol w. Next are the integers. These include the natural numbers, the negatives of the natural numbers and number 0. These are denoted by the symbol z. After integers, we had numbers in the form of fractions that gave rise to rational numbers, which are denoted by the symbol q. Then what are the numbers next to these? We will study about those in this module. So in this module, we will cover the given subtopics: irrational numbers and real numbers and their decimal expansion, converting recurring decimal numbers in the form of p by q, plotting of irrational numbers on number line, square root spiral, and let's revise. We know that rational numbers are of the form p by q, where q is not equal to 0. All natural numbers, whole numbers and integers can be written in the form of p by q, where q is equal to 1. For example, 7 can be written as 7 by 1, minus 2 can be written as minus 2 by 1, and so on. Therefore, all these numbers are also the rational numbers. Know more about rational numbers in our video on rational numbers. Now, have you ever heard of the numbers root 2, root 3, root 7, etc.? Or the famous number pi? All these numbers fall in yet another category of numbers called the irrational numbers. Clear from the name, the irrationals are the numbers that are not rational. These are denoted by the symbol q dash. No rational number is an irrational number and no irrational number is a rational number. We have learned that rationals and irrationals are complementary to each other. They together form the complete broader category of numbers called the real numbers, which are denoted by the symbol r. So rational numbers plus irrational numbers gives real numbers. Let's now try to perform the division of 3 rational numbers and convert them into decimals. Dividing 33 by 6, we get 0 remainder and the decimal expansion is 5.5. Now dividing 1 by 3, we see that the remainder repeats and the decimal expansion goes non-ending. Now on dividing 1 by 7, we see that the remainder again repeats and the decimal expansion is again non-ending. But here, instead of a single number, a block of digits is repeated. So here we get two types of decimal expansions. The first one, where the remainder is 0, we term it as terminating decimal expansion, since it terminates means it stops. In the second case, the type of decimal expansion where the remainder is never 0 and the decimal expansion goes on and on, forming a pattern, is termed as non-terminating recurring. So this forms another definition for rational numbers. So rational numbers are the numbers whose decimal representation is either terminating or non-terminating but repeating, or you can say recurring. In the number 3.4568790, though the digits after the decimal are too many, but they stop, means they terminate. So this is a rational number. Now in the number 5.67676767, the digits after the decimal goes on and are non-terminating. But can you see here that they form a pattern? Or the block of digits here, that is 67, repeats. So this is a rational number too. Instead of writing long numbers as these, we usually put a bar above the repeated unit. So we can write this number as 5.67 with the bar above 67. On the other hand, there are numbers whose decimal representation is non-terminating, non-repeating, and they do not form any pattern. For example, the true value of pi is 3.14155926535897932, which never ends and does not form any pattern. Similarly, the value of root 2 is 1.414 and so on, which never ends and does not form any pattern. All the numbers that are not perfect squares, their square roots are irrational numbers. For example, root 2, root 7, etc. No irrational number can be written in the form of p by q, where q is not equal to 0. Since real numbers include both rationals and irrationals, so decimal expansion of real numbers can be either terminating or non-terminating, which is further classified as repeating and non-repeating. We have learned how can we convert p by q into decimal form. Here we will know how can we convert the decimal form into p by q form. Let's take the same example, 0.3 bar. We write it as 0.333 and so on. Let's take it as x. अब जो डिजिट रिपीट हो रहा है मुझे उसे डेसिमल के लेफ्ट हैंड साइड पे लेके आना है. Since only one digit 3 is repeating, तो ऐसा क्या करें कि 3 डेसिमल के लेफ्ट साइड पे आ जाए? Yes, we will multiply it by 10. तो मैंने दोनों साइड्स को 10 से मल्टीप्लाई कर दिया. We know after decimal we can add any number of 3's. So I get 10x is equal to 3.333, which can be further written as 10x is equal to 3 plus 0.333. Thus 10x is equal to 3 plus x, which implies 10x minus x is equal to 3, which gives 9x is equal to 3, which at last gives x is equal to 3 by 9 equals to 1 by 3. Thus, p by q form of 0.3 bar is 1 by 3. Now, this was our number line. We have learned how do we represent integers on it, how do we represent fractions on it, or how do we represent the decimals on it. Have you ever wondered that how can we represent the numbers root 2, root 7, etc. on this number line? Where will they lie? Let's try to represent root 2 on the number line. On the number line, we will draw a triangle with unit base and unit perpendicular. But where we will draw this? We take the base on the interval 0 to 1 and name it as BC. At 1, we draw unit perpendicular and name it as AC and then join AB, which is the hypotenuse. We will here make use of the Pythagoras theorem. This theorem states that in a right angle triangle, the square of the hypotenuse side is equal to the sum of the squares of the other two sides. So we have AB square is equal to AC square plus BC square, which is equal to 1 square plus 1 square equals to 2. So AB is equal to root 2. That is, hypotenuse is equal to root 2. Yay! We have found the number root 2. But how do we now represent it on the number line? We now measure the distance of the hypotenuse AB, and with the same distance we mark an arc on the number line from the point 0. This marking on the number line is the number root 2. In the next example, let's try to plot root 5 on the number line. To show root 5 on number line, firstly we will find the other two numbers whose result will be root 5 satisfying the Pythagoras theorem. We know that whole root of 2 square plus 1 square is equal to square root 5. So we'll proceed further. तो एक नंबर लाइन ड्रॉ करो, ओरिजिन से 2 यूनिट के डिस्टेंस पे पॉइंट A मार्क करो. अब पॉइंट A से यूनिट लेंथ का परपेंडिकुलर लाइन सेगमेंट AB ड्रॉ करो. By Pythagoras theorem, the distance OB is root 5. अब ओरिजिन को सेंटर लेके एंड OB को रेडियस लेके एक आर्क ड्रॉ करो जो नंबर लाइन को पॉइंट P पे कट करे. This distance OP will represent √5 on the number line. Now see this triangle with unit base and unit perpendicular. We know that by Pythagoras theorem its hypotenuse is √2. I now consider √2 as base and draw unit perpendicular to this to form another triangle. Again by Pythagoras theorem we get hypotenuse of this formed triangle as √3. Again taking √3 as base and drawing unit perpendicular to it and again applying Pythagoras theorem, we get its hypotenuse as √4. Continuing this further by drawing perpendiculars to the hypotenuse of the previous triangles and applying Pythagoras theorem, we get a beautiful spiral-like structure depicting the further roots as √5, √6, √7, etc. This is known as square root spiral. Let us suppose we want to plot 2.665 on the number line. We know that this number lies between 2 and 3. So look closely on the portion between 2 and 3. Suppose we divide this portion into 10 equal parts. 2 के राइट में पहला मार्क होगा 2.1, दूसरा 2.2 and so on. Now we know 2.66, 2.6 और 2.7 के बीच में लाई करेगा. So we magnify the space between 2.6 and 2.7 with the help of the magnifying glass and again divide it into 10 equal parts. First part will be 2.61, second will be 2.62 and so on. Now 2.665 will further lie between 2.66 and 2.67. Let us focus on this portion of number line and divide it again into 10 equal parts. The first one will be 2.661, second will be 2.662 and fifth mark will be 2.665. So this was our required number. Such process is known as the process of successive magnification. Let's now revise what we have learned. The first question is, which of the following numbers is irrational? √81, √12 by √3, √4 by 9 or √5? The answer is √5. The second question is, are the square roots of all positive integers irrational? The answer is no. As for example, square root of 4 is 2, but it is not an irrational number. The third question is, how many irrational numbers are there between any two rational numbers? Yes, you are right. There are infinitely many irrational numbers between any two rational numbers. The last question is, to represent irrational number on the number line, we take help of which theorem? The answer is, to represent irrational number on number line, we take the help of Pythagoras theorem. So here we come to the end of this module. In the next module, we will study more on real numbers. This is Priyanka signing off. See you later in next videos. Till then, keep learning, keep sharing. Thank you.